In the last video, we defined the dimension of a vector space to be the number of elements in a basis. But we did mention that since a vector space has tons of different bases, there was the result to be proven to show that the dimension was well defined. So what we have to prove is the following theorem. Assume that B, which is V1 through Vn, is a basis for V. I want to show that any basis B1V has exactly n elements. And so the dimension would be n and would be well defined. We will prove a couple of other results on the way to proving this. We'll also prove that if S inside V has n m elements, so more elements than the basis, then S is linearly dependent. So you can't have 4 linearly independent vectors in R3 because a basis for R3 would have 3 elements in it. And on the opposite side, if T has fewer elements than V, then span of T cannot be all of V. So I'm going to write it as a proper subspace. It's contained in V, but it isn't. It cannot be equal. All right, so let's prove this. I'm going to take S to be V1. Oh, let's put W right here. W1 through Wm with n elements, and we're assuming that m is bigger than n. We need to show that S is linearly dependent. So we need to find a linear combination that gives us 0. So for each I, Wi, this element of this subset here is in V, so it is in the span of our basis V, and so that means that Wi is equal to some linear combination, so B 1 V1 plus B2 V2 plus Bn Vn. These coefficient will depend on I, and so let me add an index here to make sure that we have a good notation for each linear combination. All right, so I want to prove that the Wi's are linearly dependent, so I need to consider 0 V to be equal to A1 W1 plus AN WN. All right, so this is going to look a bit like those problems we were doing where I gave you a set that was linearly independent and I ask you to tell me whether a set of linear combination would also be linearly independent. And so here we know that this set here is linearly independent, and now we want to know, well, if I write these, will it still be linearly independent? All right, so I'm going to replace each W by its linear combination. Sorry, there's M of these. So this is M, 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 and M. Let me rewrite this, it's confusing. So AM, B1, M, V1, B, N, M, Vn. All right, we got it. All right, so just like we did in those examples that I mentioned, we put all the V1s together. So we'll have big thing times V1. The terms for V1 will be A11, B11. I'll have A1, A1, A2, B12, and the last one will be this one, AM, B1M. And we'll have something similar for Vn. So we have A1, Bn1 plus AM, Bnm, Vn. All right, so now we know that these vectors are linearly independent. So since V1 through Vn is linearly independent, this would only happen if all of the coefficients were 0. So A11, B11, A2, B12. Oh, sorry, I keep wanting to put an extra 1 here. That needs to be equal to 0. And A1, Bn1 plus A2, Bn2 plus AM, B, and M, that has to be equal to 0. All right, so I'm getting, these are all real numbers now, so I'm getting a linear system in A1 through AM. So I'm getting a linear system that has n rows and m columns in terms of A1, A2, AM. So the first row is for B1, B12, B1M, and then I'll have Bn1, Bn2, Bnm. And I want this to be equal to 0. All right, sorry for the confusion with the indices. Hopefully everything is clear now. At this point, we're going to use the fact that m is bigger than n. So as m is bigger than n, the system has a free variable, at least one. System is consistent. And so there is a non-zero solution. And so the set we started with, this set S here is linearly dependent. All right, so notice that nowhere in this proof are we using the fact that B is a basis. We only need that we could write the elements of W in it. So really, we prove that if span of S is equal to span of U, so U is here to replace B. I don't want to use B because B is for basis, so it does hint at something more specific. If the two spans are the same, but if you have more elements in S than you have in U, then S is linearly dependent. All right, that's the key right here. Perfect. Now let's move on to 2. I want to prove that if T is inside V, has K elements where K is less than M, so a smaller subset than this, then the span of T cannot be all of V. All right, so I'm going to take T inside V with K elements where K is less than N. All right, so we're going to show that the span of T is inside V but is not equal to V. And we're going to do a proof by contradiction. So that means we're going to assume exactly the opposite of what we're trying to prove, and we'll see that it makes no sense. We get a contradiction. So we're going to assume that the span of T equals to V, and so it's equal to the span of B. Then we have that the span of T equals span, sorry, let me write it the other way so it looks the same as what we have above. Span of B is equal to span of T, and then B, that has n elements, that's more than the number of elements in T, which is K. All right, so we have exactly what we assumed up here. And so B is linearly dependent. But that's a contradiction because B is a basis. All right, so if we assume that span of T is V, we get a contradiction. And so span of T is inside V, but not equal. All right, so we're already using this to show that B1 also has n elements. All right, so case number one, number of elements of B1 is bigger than n. All right, so if it has more than n elements, then by 1, S equals B1 is linearly dependent, but that contradicts B1 being a basis. And so what we get is the number of elements in B1 cannot be more than n. All right, let's look at the second case. What if we have fewer elements in B1 than we had in B? Well, that's covered in 2. By 2, T equals B1 cannot span all of V. Otherwise, B would have redundant vectors. Otherwise, B would be linearly dependent. And so, which is contradiction. And so the only thing that's left is case number 3, which says that the number of elements in B1 is actually n. And that's what we wanted to prove. All right, so at this point, we've proven that any basis has exactly the same number of elements. And so that means the dimension makes sense. That means the definition that we had for dimension in terms of number of elements in any basis, that makes sense.